Hello everyone, I am Dr. PSV Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the intrinsic semiconductors. Generally, the electrical resistivity or conductivity of a solid varies in between the conductivity of conductors and insulators. Say such kind of materials are said to be semiconductors. Anyhow, at the end of this lecture, student will able to understand the crystal structure of intrinsic semiconductors, and he can able to derive the electrical conductivity expression and Fermi level expressions also. So now coming to the semiconductors, actually the semiconductors are classified into two categories as intrinsic and extrinsic semiconductors. Intrinsic semiconductors are pure form of semiconductors. The pure semiconductors like silicon and germanium, they are called intrinsic semiconductors. Now coming to the crystal structure of an intrinsic semiconductor. Silicon, the atomic number 14. So coming to the electron configuration, 1s2, 2s2, 2p6, 3s2. Actually we write 3s1, 3p3. So these 10 electrons are tightly bound to the nucleus, whereas these 4 electrons are the valence electrons. Actually they are not free electrons in silicon. These 4 electrons will form 4 covalent bonds with the neighboring silicon electrons. Observe, each silicon atom containing 4 valence electrons. These electrons are forming 4 covalent bonds with the neighboring silicon electrons. So this figure A is representing the crystal structure of silicon. In the same way, germanium also, each atom is containing 4 valence electrons. They are participating 4 covalent bondings. That's why there are no free electrons in the silicon crystal. So at T is equal to 0 degree Kelvin, this is the crystal structure. There are no free electrons, no free holes, nothing at all. That's why even this material also behaves like an insulator at 0 degree Kelvin. Other than 0 K, okay, electrons will go to the higher levels. Okay, we shall discuss. Now coming to the energy band diagram. Say there exist 3 energy bands in this one. The lower energy band is the valence band. The upper unfilled band is the conduction band. In between these two, there is a forbidden band or the energy gap Eg. Here, at T is equal to 0 degree Kelvin, the valence band is completely filled with electrons, no free electrons at all, and conduction band is completely empty. That's why if this material is connected to the external circuit, as there are no free electrons in this one, it cannot conduct the electricity. It is acting like an insulator. Other than 0 K, what happens? As the temperature is rising, if T not equal to 0 K, because of the rupture of covalent bonds, some free electrons will be available. Means, as we increase the temperature, electron will go to the conduction band, and one electron is present in the conduction band. There is a deficiency of electron, nothing but hole. And one more electron goes to conduction band, one more hole is created. In that way, electrons will go to the conduction band, creating the holes in the valence band. So the electron density is denoted by N, holes density is denoted by P. Say, the number of electrons is equal to number of holes. At any temperature, electron density is equal to holes density. It is denoted by Ni, called intrinsic density. Electron density, number of negative charges is equal to number of positive charges. Charge is neutralized, charge balance is taking place. Anyhow, I am going to explain or derive the expression for the Fermi energy level, where the Fermi level lies. If you observe this diagram, Fermi level is lying exactly at the center of the forbidden energy gap. Of course, how do we derive this one? Already I am saying N is equal to P is equal to Ni. Number of electrons is equal to number of holes at T not equal to 0 K or T greater than 0 degree Kelvin at any temperature. Now coming to the same, N is equal to P is taken. The electron density expression, it is given by 2 into, actually N is equal to Nc into e power minus of Ec minus Ef by Kt. Similarly, you can write P is equal to Nv into e power minus of Ef minus Ev by Kt. You observe, say the upper edge of the valence band is taken as Ev, lower edge of the conduction band is taken as Ec. Nc is called density of available energy states, effective density of available energy states in the conduction band. C stands for conduction band. Nv, the effective density of available energy states in the valence band. V stands for valence band. At any temperature N is equal to P, it is equal to Ni. Of course, Nc expression is there, that is given by 2 pi me star kT by h square whole power 3 by 2 e power minus of Ec minus F by kBt or kT, where kB Boltzmann's constant T absolute temperature. So me star the effective mass of the electron. Here h Planck's constant. In the same way RHS you observe 2 into 2 pi mp star kBt by h square whole power 3 by 2 e power minus of Ef minus Ev by kBt. Now 2 and 2 cancelled, and just rearranging the terms, except me star and mh star, the remaining terms are same in this Nc expression. That's why those things will be cancelled. Here we are writing me star whole power 3 by 2 e power minus of Ec minus Ef by kT, it is equal to mp star whole power 3 by 2 e power minus of Ef minus Ev by kT. Actually me star the effective mass of the electron in the conduction band, mp star it is the effective mass of the hole in the valence band. So anyhow, writing this term in the LHS and me star in the RHS, what do you get here? E power minus of Ec minus Ef by kT divided by e power minus of Ef minus Ev by kT, it is equal to mp star whole power 3 by 2 by me star whole power 3 by 2. Again simplifying this one, e power something is equal to mp star by me star whole power 3 by 2 we are getting. Okay, this is e power something, just let us take the logarithms on both sides, natural logarithms. So that is given by taking the logarithms, you will get ln. Ln means natural logarithm, log base e. So you will get this as Ef is equal to Ec plus Ev by 2 plus 3 by 4 kBt ln mp star by me star at any temperature T greater than 0 K. So this is the expression for the Fermi energy level at T greater than 0 degree Kelvin in an intrinsic semiconductor. Suppose let us take T is equal to 0 K. At 0 degree Kelvin what happens? See the second part of this equation, K by 3 by 4 kBt ln something. So that T is taken as 0. We get this as Ef is equal to Fermi energy level is equal to Ec plus Ev by 2. Simply what is Ec in this one? Ec is the lower edge of the conduction band, Ev the upper edge of the valence band. That's why we are getting Ef is equal to Ec plus Ev by 2, or else we can write this as Ef is equal to Eg by 2. Fermi energy level is lying exactly at the center of the forbidden energy gap. At T is equal to 0 K, this is the expression. At other than 0 degree Kelvin or more than 0 degree Kelvin, we get Ef is equal to, this is the expression. So simply what we are taking in this one is, this is the crystal structure. At any temperature other than 0 K, some electrons have been promoted to the conduction band, but the number of electrons in the conduction band is equivalent to number of holes in the valence band. So automatically we get N is equal to P, electron density is equal to holes density, just substituting expressions for N and P, and on simplification we are getting Ef is equal to Ec plus Ev by 2 plus K 3 by 4 kT log mp star by me star, and taking T is equal to 0 degree Kelvin, it is Ec plus Ev by 2 or Eg by 2, the Fermi energy level. This is the expression for Fermi energy level. Now coming to the electrical conductivity of an intrinsic semiconductor. Actually what we are taking is, at any temperature T greater than 0 degree Kelvin, some electrons are promoted to the conduction band, some holes are created in the valence band. Hole is nothing but deficiency of electron. Anyhow, coming to the semiconductor slab. So at any temperature T greater than 0 degree Kelvin, above 0 degree Kelvin, there are some electrons and holes in the semiconductor. This is connected to a battery like this. When the electric field is applied, what happens? Electrons are traveling towards the positive terminal, holes are moving towards the negative terminal of the battery. That means both the charge carriers are producing the electrical conduction. Means this semiconductor, intrinsic semiconductor, is said to be, the conductivity is bipolar. Because of two types of polarities, the conductivity is there. So let us write the total current I is equal to IE plus IH. The total current, it is due to The current due to electrons and also holes, I suffix E stands for current due to electrons, IH current due to holes. What is the current density? Total current density J is equal to JE plus JH. We know one thing, J is equal to I by A, the total current per unit cross sectional area. That's why I is equal to IH or J is equal to JH we can write. Actually, for the current density, we have an expression J is equal to NE into VD, drift velocity, or else NE into mu E, mobility into electric field. Same thing is written here, J is equal to NE mu E into E plus PE mu H into E. Actually, mu E, mu suffix E, this is the mobility of electrons, mu H is the mobility of holes. I want to write J by E, the electrical current density divided by electric field vector, capital E bar. This is denoted by sigma, that is called electrical conductivity. Therefore, what we get here? NE mu E plus PE mu H. This is the expression for the electrical conductivity in case of an intrinsic semiconductor. But one thing we know, at any temperature, electron density is equivalent to holes density. N is equal to P, it is equal to Ni. So, we can write like this. Therefore, on simplification, we get sigma is equal to Nie into mu E plus mu H. What is this Ni? This is the intrinsic carrier concentration, intrinsic carrier density. Small e, charge of the carrier, that may be electron or hole. Quantity is same. Electron charge is negative, hole's charge is positive. And mu E, mu H are mobilities of electrons and holes. This is the expression for the electrical conductivity in an intrinsic semiconductor. So, coming to the summary of this one, actually in this article what we have seen is the crystal structure of an intrinsic semiconductor. See, this is the crystal structure of either silicon or germanium, and how the valence electrons are in the formation of covalent bonding we have seen. And corresponding to that one, what is the energy band diagram we have seen. Later, we have derived the expressions for electrical conductivity and also the Fermi energy level expressions. See, the Fermi energy level expression, taking N is equal to P is equal to Ni, we got Fermi energy level EF is equal to EC plus EV by 2 plus something. At T is equal to 0 K, we got EZ by 2, means at the center of the forbidden energy gap, the Fermi level is lying at T is equal to 0 K. And taking the bipolarity, means electrons and holes are producing the current, the total current density or the total electrical conductivity Nie into mu E plus mu H. That what we have derived in this article. Thank you very much.